we have learned that if an enolate reacts with an aldehyde or a ketone, nucleophilic addition on the aldehyde or the ketone results, the initial product is beta hydroxy carbonyl compound. Beta hydroxycarbonyl compounds can undergo elimination reactions if they are treated with catalytic base or even with an acid to give alpha beta unsaturated carbonyl compounds. Now, once the enolate or an enolate is formed from a carbonyl compound, if it's treated with another electrophile, okay, different from aldehydes and ketones, and if somebody asks what are the typical organic electrophiles, of course you would think of alkyl halides, you'd think of aldehydes and ketones, but not only that, we should think also of carboxylic acid derivatives. So if an enolate reacts with a carboxylic acid derivative, such as an acid halide, for example, or acid anhydride or an ester, then a different reaction takes place. Let's see an example of that type. So if we take ethyl acetate, for example, ethyl acetate, which is, if you look carefully at the structure, you would see it is actually an ester. If this ester is treated with catalytic base, so if you react this with catalytic sodium ethoxide, again, this catalytic sodium ethoxide should make a very small amount or catalytic amount of the corresponding enolate. We can show that mechanistically. So this is the ethoxide ion. The ethoxide ion can come, take off this hydrogen or hydrogen at the alpha position. So that's the alpha position again, or the alpha carbon. Of course, remember, esters are acidic at that alpha position. That's because the corresponding alpha carbon ion can undergo resonance to give the corresponding enolate. That's exactly why they are acidic. pK is about 20, 25. Under these catalytic conditions, a catalytic base can deprotonate the ester to give a catalytic amount of the corresponding enolate. So the base takes off this hydrogen. The hydrogen carbon bond is broken to make a double bond here, and the carbon oxygen bond is simultaneously broken to give this enolate. This is the ester enolate now. Now, catalytic amount of the enolate can react with a similar amount of the ester that is unreacted still. Of course, if there's 0.01, again, if there's 0.01 mole of the base, 0.01 mole of the enolate should form, 0.99 mole should be left unreacted. So 0.01 mole of the enolate can react with another 0.01 mole of the ester. But this time, the reaction course will be different, or the path will be different from that observed in the aldol reaction. Of course, in the aldol reaction, the enolate at this stage reacts with the aldehyde with an aldehyde or a ketone. In this case, there is no aldehyde or a ketone, but there is an ester. And of course, an ester is a carboxylic acid derivative. And of course, if you remember, the reaction type is of carboxylic acid derivatives is different from that of aldehydes and ketones. Let's see what we can do. If you take that ester, this is the ester enolate, sorry. This is the another amount of the ester. So the enolate can come. The enolate comes, it attacks this ester, of course, at that carbon. That carbon is electrophilic due to inductive effect and resonance. The carbon-oxygen double bond is broken. It's reformed with elimination of the OET minus, if you like, the alkoxide. It's a potential leaving group. And of course, this reaction type is very distinct. It is, if you recall, it is a nucleophilic acyl substitution reaction, typical reaction of carboxylic acid derivatives. And that's where carboxylic acid derivatives are different from aldehydes and ketones. Of course, aldehydes and ketones undergo nucleophilic addition type. Carboxylic acid derivatives undergo nucleophilic acyl substitution reaction type, the product that's obtained is the following. So this is the product. Remember, that's the alpha position. That's the alpha position. This unit comes from the enolate, and this unit comes from another amount of the ester. If you look at this product, you would notice it's actually a beta ketoester. It's a beta ketoester that's obtained as a result of this condensation reaction between, if you like, of an ester, of course, where an enolate of an ester reacts with the ester itself. It's a condensation reaction. This reaction is called Claisen condensation reaction. So the Claisen condensation reaction makes a beta keto ester, an enolate of an ester reacts with the ester itself. The reaction type is a nucleophilic acyl substitution reaction, and of course the product should be a very useful one. The reaction is called Claisen, and the Claisen reaction, to summarize it, the Claisen reaction is a reaction between an enolate with a carboxylic acid derivative to give a 1,3 dicarbonyl compound. So this is a 1,3 dicarbonyl compound, specifically it's beta keto ester. So the Claisen reaction again is a reaction between an enolate and an ester to give 1,3 dicarbonyl compound. The reaction type is a nucleophilic acyl substitution reaction.